Fluid pressure. The pressure at any given point in a fluid is the same in all directions. Pascal law. We may prove this by considering the equilibrium of an infinitesimal triangular prism of fluid as shown in this picture. The fluid pressure normal to the faces of the element are P1, P2, P3 and P4. P1, P2, P3, P4 and also P4 with force equal to the pressure times area. So this is a force F1 for example. The equilibrium of force in x and y direction gives this relation. In the x direction, P1 dy dz, P3 ds dz, multiply to sinus theta, and in the y direction this direction, P2 dx dz, P3 ds dz cosinus theta. Since ds sinus theta ds sinus theta equals to dy and ds cosinus theta equals to dx. With substitution to this relation, we can obtain P1, P2, P3, P. By rotating the element through 19 degrees, we see that P4 is also equal to the other pressure. Thus, the pressure at any point in a fluid at rest is the same in all directions. In this analysis, we need not account for the weight of the fluid element because when the weight per unit volume is multiplied by the volume of the element, a differential quantity of third order results which disappear in the limit prepared with the second order pressure force term. In all fluids at rest, the pressure is a function of the vertical dimensions. In all fluids are at rest, the pressure is a function of the vertical dimension. To determine this function, we consider the force acting on a differential element of vertical column of float cross-sectional area dA as shown in the picture here. Let me write again. As we said, in all flows, rest pressure is a function of the vertical dimension only. Consider this picture. The positive direction of vertical measurement h is taken downward. Positive. The pressure on the upper face is P, and that on the lower face is P plus the change in P, or P plus dP and P. The weight of the element equals to rho g, as shown here also, this arrow. The normal forces on the lateral surface, which are horizontal and do not affect the balance of force in the vertical direction, are not shown. Equilibrium of the fluid element in the h direction requires this relation. P dA rho g dA dH P plus dP dA equals to 0. We can eliminate these two and also this. At the end, we can obtain dP equals to rho g dH. This differential relation shows us the pressure in a fluid increase with depth or decrease with increased elevation. This equation holds for both fluids and gases and agrees with our common observation of air and water pressure. Fluids, which are essentially incompressible, are called liquids, and most practical purpose we may consider the density rho constant for every part of the fluid. Which are essentially incompressible are called liquid. And rho is constant. Constant everywhere in the fluid. So we have this relation rho GH. The pressure P0 is the pressure on the surface of the liquid at H equals to 0. If P0 is due to atmospheric pressure and this measuring instrument records only the increment above atmospheric pressure, the measurement gives the gauge pressure. If P0 is due to atmospheric pressure, on the surface of the liquid, and the measurement instrument records only the increment above atmospheric pressure. The measurement gives what is called gauge pressure. The common units for the pressure in the SI unit SI kilopascal, which is the same a kilonewton per square per meter. In computing pressure, if we can use another dimensions. In the US customary pressure, float pressure is generally expressed in pound per square inch square. Kilonewton or the next section is hydrostatic pressure on submerged rectangular surface.